Good morning, my dear students. In the last class, we have discussed about the Helmholtz galvanometer in detail about its what it is the principle, construction, or theory of the Helmholtz galvanometer. Now, let us come to the next point, that is the magnetic properties. Here, you see, every magnet or a magnetic, what it is the material, it is having its own, what it is the properties, isn't it? And those properties exhibited by the magnet or magnetic material known as the magnetic properties. Now, let us try to understand what are those important properties a magnet and magnetic material exhibits or has. Now, first, let us try to understand regarding the magnetic dipole. Now, here, the title itself explains that magnetic dipole. Dipole is what it is, which is having the two poles, isn't it? That is, this shows that every magnet, it has the two poles, and moreover, you are well familiar, isn't it, about the magnet, isn't it? That magnet, it has the two poles, that is north pole and what is the south pole, isn't it? Now here, if you consider this is a what it is the bar magnet, isn't it? Then this magnet has got the two poles, north pole and south. And here, every pole has got what it is of some strength of magnetism in it. Isn't it? Every pole, it has some what it is a strength of magnetism in it, that is pronounced as what it is a pole strength. Isn't it? Now that pole strength, symbolically, it is represented as pole strength is equal to what? Yeah. And the pole strength of what it is the north pole is taken as positive, because in the lower classes you have studied that in a magnet, whatever the two poles, that is north pole and south pole are there, in that north pole is taken as positive and south pole is taken as the negative. And it's what it is the pole strength, that is the pole strength of the north pole is taken as positive, the pole strength of the south pole is taken as the negative. Next is the distance between the two poles, this one. It is represented by usually what it is the 2L, and this distance, it is called as what is the magnetic length, isn't it? Magnetic length. Now this magnetic length, it is represented by what is the 2L. That is, what is the magnetic length? The distance between the two poles is what it is known as the magnetic length. Now, coming to the magnetic dipole here, is it? What is the definition of? Is it? What it is the dipole? Then usually we saw that dipole means what? Which is having the two poles. Is it, to understand? Yeah. But the definition is that the definition of the dipole is the two poles or two unlike poles of equal strength separated by some distance is known as the magnetic dipole. That means two unlike poles, meaning is that they must be unlike or they are opposite in nature. In this case, north pole is positive, south pole is negative, so that they are opposite in nature and of equal what it is the strength. That is the pole strength of north pole and south pole, it is same, but the pole strength of north pole is positive, south pole is negative, isn't it? And that is two unlike poles of equal strength separated by some distance, isn't it? But the condition is that then these two poles must be separated by some distance. That is known as the magnetic dipole. Once again, I repeat here. Two unlike poles of equal strength separated by some distance is known as magnetic dipole. And the strength of the each pole is known as the pole strength, represented by small m, and the distance between the two poles is known as the magnetic length. It is represented by 2L. And there is one more point in this one. It is a magnetic moment. Magnetic moment. Then this magnetic moment, symbolically, it is represented by capital M, and it is equal to the product of the pole strength and magnetic length, is it? Yeah, into L. Then this what it is the product, it is known as what it is the magnetic moment. Isn't it? Now listen here, one more point I want to make it clear for all of you is that any material, isn't it, or either it is a magnet or a magnetic material, if it wants to exhibit the magnetism, isn't it, or the magnetic field, then it must have compulsory, it must have magnetic moment. If there is no magnetic moment, then it will not exhibit any magnetic property, means it will not exhibit any magnetic field. Because, isn't it, in the what it is the last class, isn't it, we have discussed, isn't it, the what it is the field at a point due to a what it is a strike conductor, magnetic field, isn't it? Then this is equal to what? This is equal to the mu naught divided by 2 pi into I divided by TL, etc. Then from those you can understand that here every what it is the magnet, it produces the magnetic field whenever it has got some magnetic moment. Isn't it? If there is no magnetic moment, then it will not produces any magnetic field. Are you following? Now this is one. And next is one more. The magnetic moment, it is a vector. Isn't it? Means it has got the magnitude as well as the direction. Isn't it? Then here this what is the, by using this one, isn't it, m into 2l, you can calculate what is the magnitude of the magnetic moment. Then what about its direction? Isn't it? The direction of the magnetic moment is from what it is the south pole to what it is the north pole. Isn't it? The magnetic moment of this is what it is the in this direction. It is. Then this is about what is the magnetic moment. Isn't it? The next is here, one more thing is the examples for this dipole or magnetic dipole are what? One is the bar magnet, isn't it? And another is the what is the a circular loop carrying the conductor, isn't it? Bar magnet, isn't it? Since it has got the two poles, north pole and south pole, therefore it is a dipole. And these two are separated by some distance, hence it is a magnetic dipole. This is one. And second thing is what it is a circular loop carrying what it is a current. Now here, when you consider this is a circular loop which is carrying current, isn't it? This will act like a dipole, isn't it? Now, in the previous class we have discussed that according to the magnetic effects of electric current, whenever the current flows through any conductor, then the magnetic field is produced around the conductor. In detail, we have discussed how to find its magnitude, direction, all those things, isn't it? I don't want to go in detail again about those. But this is a circular loop or circular conductor. When it carries the current, then it produces the magnetic field. If it is producing the magnetic field, means it acts like a magnet, isn't it? Electromagnet, and that also we have discussed that it is a non-permanent, etc. Now, since it is acting like a magnet means, then a magnet has got the two poles, north pole and south pole, isn't it? Now, how to identify that? Isn't it? In this circular loop carrying the current, isn't it? Then it acts like a magnet means, then which is the north pole and which is the south pole, isn't it? Now, to understand this one, now let us consider here, this is a circular loop. If the current in the loop is in clockwise direction, like this, isn't it? Now, here, the direction of the current is like this, isn't it? Here, the direction of the current is like this, isn't it? These two are arrows. Now, tails, you join the tails. Like so. Now, how it looks like to you? Then it looks as S type. S type means, now this phase of the circular loop, it acts like a south pole and its opposite phase will act like a north pole. That is, when you consider a circular loop of thickness like this one, when the current is clockwise, isn't it? Then this phase will act like a south pole and its opposite phase will act like a north pole. And the thickness of the loop, whatever it is there, that is the distance between the two poles. The next is, suppose if the current is in anti-clockwise direction, isn't it? Now, let us consider in anti-clockwise direction now. Now, here, direction of the current is like this, and here, direction of the current is like this. Again, you join the tails. Now, it looks like a N type, means this phase of the coil act like a north pole and its opposite phase will act like a south. Therefore, it shows that a circular loop carrying the current, it acts like a what is the dipole, that is, which has got the two poles, north pole and south pole. And how to identify which is the north pole and south pole? It depends upon what direction of the current in the circular loop. Whether if it is a clockwise, is it the phase of the loop is it towards the observer? We say is it when you look at from here, this is the towards the observer. Towards the observer, phase of the loop towards the observer is south pole. Opposite phase act like a north pole. If the current is in anti-clockwise direction, then the phase of the loop towards the observer acts like a north pole and its opposite phase will act like a south pole. Isn't it? Now see, this is what dipole, isn't it? Now listen here. Yes, we are having that is in magnetism, isn't it? The magnetic dipole, that means it has got the two unlike poles, isn't it, of equal strength separated by distance is known as the magnetic dipole, isn't it? And what is the pole strength and what is the magnetic length and magnetic moment, isn't it, etc. In a circular loop, when there is a current, it acts like a dipole and means it has got the two poles. Then how to determine which is the south pole and north pole depending upon the direction of the current, that we have discussed in detail, isn't it here. Now after understanding this one, for your information, listen here, for your information it is, isn't it? Then this I want to mention you that then in your studies, isn't it, you have come across what it is the electricity as well as in the magnetism also. Now there is no much difference between electricity and magnetism. As you are having in magnetism two poles, north pole, south pole, isn't it? North pole is taken as positive, south pole is taken as negative. In electricity, isn't it? Instead of the magnetic poles, you are having the electric charges, isn't it? Then electric charges are also of two types, then positive charge, negative charge, isn't it? And here you are having the magnetic dipole here, isn't it? You are having the electric dipole also, isn't it? That is two unlike charges, that two unlike poles we are using here. Two unlike poles of equal strength separated by some distance is the magnetic dipole. Similarly here, two unlike charges, means one is positive, negative, of equal strength. It is, that means they must have same amount of charge, isn't it? Then unlike charges of same amount separated by some distance, it is what is the electric dipole, isn't it? And the next is here in case of the magnetism, it exhibits or it produces a magnetic field, then here it produces the electric field, isn't it? Magnetic intensity, electric intensity, magnetic flux, electric flux, like that, isn't it? In general, isn't it? Whatever the properties a magnetism has, then the same properties are present in the electricity also, isn't it? But there is only one difference is there between this electricity and magnetism. What is that difference means? This I want to make it clear, isn't it, for all of you? Listen here, seriously listen. Yes, in case of the electricity, you are having the what is the two unlike charges means positive charge and negative charge, isn't it? And at the same time, then you can get, isn't it, separately positive charge and negative charge. Negative charge is the electron, isn't it? Negative charge, it is the electron. Independently, you will get electron. The ion, which is deficient electron, isn't it? Electron deficient, it is a positive charge. That means in electricity, isn't it? You will have what is the separate what is the positive charge and negative charge. Then even you can take electron and proton, isn't it? Electron is negatively charged particle. Proton is a positively charged particle. Separately you will get, but that situation it is not there in the magnetism, isn't it? In the magnetism, then no doubt you are having the north pole and south pole, but if you want an independent north pole and south pole, you never get it, Isn't it? Always, isn't it? Magnetic poles exist in pair only, isn't it? Now, suppose some of you might want to think that this is a bar magnet, isn't it? North pole and south pole. If I divide this into two parts, isn't it? This is north pole and this is south pole. Will you get it? No, isn't it? Even if you break like this one, if this is the south means immediately north pole is created here, and if this is the north pole means south. Even if you want, isn't it? If go on break into smaller and smaller and smaller pieces, then but you never get an independent what is the magnetic pole. Isn't it? Then so that we say the what it is the monomagnetic pole does not exist in the nature. That means an independent magnetic pole does not exist in the nature. But independent what is the electric charge is existing, but that will not happen in case of the magnetism. This is only what is the difference between the electricity and magnetism, isn't it? Now, this is what the about what is the magnetic dipole. Now, after understanding this one, now we will go to the next property is the magnetic field. Second property is magnetic field. Now here, the way in which you have what it is defined the electric field in electrostatics topic, the same definition is there in the magnetism, that is the magnetic field. Now, before going to go for the definition of this magnetic field, let us take an example. Isn't it? This is a bar magnet, isn't it? Then north and south poles. Now, if it is a magnet means it produces the magnetic field like this. Now, how to realize that there is a magnetic field here? Isn't it? We can't see magnetic field with our eyes, no. But how to realize it? Isn't it? For that, what we do is then here we will put any what is a magnet or magnetic material. Now, suppose if it gets attracted, isn't it? Then we say that there is a magnetic field. Then usually the small children will play that one magnet, isn't it, and another magnet. Then they will leave, they get attracted. Isn't it? Yeah. When you put it like this, isn't it? Leave it, then immediately what it is, they will come and join. Like because of what? It is the attraction. Isn't it? That when you put it a magnet, isn't it? At this point, if it gets attracted, isn't it, towards this magnet, then we say that here there is a magnetic field. Isn't it? Not only the magnet, even if you put a magnetic material, for example, isn't it? When you put an iron piece here, then that isn't it? If it gets attracted, then you say that here there is a magnetic field. Isn't it? You want to take it this what is the magnet or what is the iron piece away and away from it. Isn't it? After reaching to some position, then what will happen is, for example, let us say when you put this magnet, isn't it, or an iron piece, it will not get attracted. Naturally, it is. It gets attracted only when you put it at a certain small distance, isn't it? Then only it gets attracted. Then suppose if it is placed a little bit away from this magnet, then it will not what gets attracted. Therefore, when if it is not gets attracted, then we see that at that point there is no magnetic field. Then when you put it here, then if it is gets attracted, then we say that there is a magnetic field. Isn't it? If it is not gets attracted, then we say that there is no magnetic field. Now, why it is gets attracted means because of the force of attraction. Isn't it? Because of the force of attraction. Now listen here. The same is it way we define what is the magnetic field. Then whatever the meaning is there here, isn't it? You put that meaning in a proper what it is the manner, you will get the or it becomes as a definition. Isn't it? Then here, what is the magnetic field means? It is the space. This is a space, isn't it? It is the space, isn't it? Around the magnet, not only here, wherever you put it, isn't it? It is the space around the magnet, isn't it? In which, isn't it? A magnet or magnetic material experiences the force. Because why it gets attracted? Because of the attractive force only. With force is attracting on this one, isn't it? Oh, because of that reason only it gets attracted. Then that force, isn't it? Acting is nothing but that magnet or magnetic material is experiencing the force on it. Because of that force only it gets attracted. Hence we say that this in this space there is a magnetic field is there. Now I will come to the main definition that magnetic field means what? It is the space around the magnet in which a magnet or magnetic material experiences the force. If it won't experience the force, then you see that there is no magnetic field. So this is the definition of what is the magnetic field. Then yeah, you know that the magnetic field, it is also be a what it is the vector quantity. It has got magnitude as well as its direction also, isn't it? Then magnitude in the different cases, isn't it? You are having the different formulas for the calculation of what is the magnetic field, isn't it? Then how to find its direction, isn't it? The direction of the magnetic field is always from south pole to the north. Like then this is what the direction of the magnetic field. Now, after studying this, what is the magnetic field? Now let us come to the next. It is nothing but the magnetic intensity. Isn't it? Third magnetic intensity. Magnetic intensity. Now there is a slight difference in definition of what it is the magnetic field and magnetic intensity. Let the definition carefully listen here word by word. Isn't it? The magnetic intensity, isn't it? Now for example, let us consider this is a magnet. This magnet produces the magnetic field up to here, isn't it? Then up to this region there is a magnetic field. Beyond this there is no magnetic field. Now the definition of magnetic intensity is that magnetic intensity at any point in the magnetic field. This is a magnetic field at this point. Is it? How much is it? Magnetic intensity is there. Like magnetic intensity at any point in the magnetic field is equal to the force. It is equal to the force acting on a unit positive pole. Once again, I repeat, magnetic intensity at any point in the magnetic field is equal to force acting on a unit north pole placed at that point. Means what you do? You place a unit north pole here. Unit north pole, or to which we call it as a unit north pole, means the north pole whose pole strength is 1 unit. 1. A north pole whose pole strength is the m, which is equal to 1. That is unit north pole. Now what you do is at this point you place, is it a unit north pole here, is it? Then whatever the amount of force acting on it, is it? That whatever the amount of force acting on that unit north pole, then that much amount of force equal to the intensity. This is the meaning of the magnetic intensity. Once again, I repeat here, magnetic intensity, is it, at any point, is it, in the magnetic field is equal to the force acting on a unit north pole at that point. Isn't it? So this is the definition of the magnetic intensity. Now the question is that here, you also know that if you are having the what it is the two magnets, isn't it, or the two poles, north pole and south pole, isn't it? In lower classes you have studied, isn't it? Unlike poles gets attracted, like poles repelled. It's what? If there is a unlike what is the poles, that is north, south pole, then there exists a force of attraction. Like poles, that is north, south pole, then there exists a repulsive force. Alright. But in general, if you are having the any two what is the poles, any two poles, then there exists a force, isn't it? Either it can be attractive or it can be repulsive. When there is attractive, if they are unlike, the force is attractive. If they are like, then force is repulsive. But there is a some force. You see? Then if there is a some force means, then how much amount of force will exist? Isn't it? Then for the calculation of that, we need a what is the formula or anything. Now that you can calculate by using one important law. That is what is that is nothing but the Coulomb's inverse square law. Then what is the Coulomb's inverse square law? Is it that already you have studied in your lower classes? Just what is to recall again what is the let us try to understand this what is the Coulomb's inverse square law. Then here, according to this Coulomb's inverse square law, let us consider there are the two poles. Is it of pole strength M1, what is the M2? Is it means like this it is. Then suppose this is the north pole and this is the south pole, and like this it is. This is the south pole and this is the north. Now the unlike poles are facing each other. Now there is this what is the attractive force. Isn't it? Now instead of this as a south, if it is not, then like poles will be there, then there is a repulsion. Like, isn't it? Now in between these two, isn't it? How much amount of force is existing? Now these two differ separated by a distance what is the d. Like that, according to the Coulomb's inverse square law, the force between the two poles directly proportional to product of their pole strength, isn't it? M1 M2 inversely proportional to square of the distance. This one. Now when you combine these two, then isn't it? You will get like this M1 M2 divided by d square. Isn't it? Now to remove this proportionality, we will put some constant. Isn't it? That is mu naught divided by 4 pi. Is it M1 M2 divided by d square. Now by using this formula, you can find, is it how much amount of force will exist between the two poles. Now then here, with the help of this formula, we can find, is it what is the magnetic intensity at any point due to a what is the magnetic pole. Now let us see here what is that formula and how we will get it that formula. Formula of magnetic intensity. Now here, let us consider this is a magnet and its pole strength is M. Now it produces the magnetic field. Now in this magnetic field, we have to find what is the magnetic intensity at the point P, which is at a distance of d. Is it from the pole? According to the definition, what is the magnetic intensity? The definition says that magnetic intensity at any point in the magnetic field, it is equal to the force acting on a unit north pole at that point. Means here you place a unit north pole. To which we call it as a unit north pole. The north pole whose pole strength is 1. It is called as a unit north pole. Now here the pole strength M is equal to 1. Is it? Then how much amount of force or whatever the amount of force is acting on this unit north pole, that much amount of force itself equal to the electric intensity. Now here, I will write here electric intensity at P is equal to what it is? Force acting on what is the unit north pole P. Now this is equal to since it is a force, you apply the Coulomb's inverse square law, isn't it? Just now we have explained force is equal to mu naught divided by 4 pi M1 M2 divided by d square, isn't it? Then that First mu naught divided by 4 pi. Pole 10, isn't it? This is one pole and this is another pole. Its pole strength is m. Whereas since it is a unit pole, its value is equal to 1 divided by square of the distance. It is nothing but it is equal to d square. Okay. Now this is equal to here mu naught divided by 4 pi. Isn't it? M into 1 is m divided by d square. Isn't it? This electric intensity at P, that electric intensity symbolically, sorry here, I use the word electric, no, magnetic intensity. Magnetic intensity, isn't it? Now, that magnetic intensity symbolically it is represented by what the B is, isn't it? Now, this B it is equal to mu naught divided by 4 pi m divided by d square. Now, what is this m? M is nothing but it is the pole strength of this pole, and this d is what distance of the point from this what is the magnetic pole. Now, with the help of this formula, you can find how much magnetic intensity it is there at any point due to a magnetic pole. Isn't it? Now, listen here. This is the very useful formula, isn't it, for what it is deriving the formulas of the magnetic intensity at any point on the axial line of a dipole, on the equatorial line of a dipole, which we are going to discuss in the next class. Isn't it? This formula, it is the most useful formula for you, isn't it? Then there you can see that we are using what it is this formula in the derivation of those what it is formulas. Next, the fourth property is the magnetic potential, isn't it? Now, what is the magnetic potential is, yes, already I had told you that there is no much difference between electricity and magnetism. What about the properties? In the electricity, it is the almost the same properties are present in the magnetism also. Then, what is the electric potential that we have discussed in the already you have studied in lower classes? That is the electrostatic. What is the topic? Now, the same way, yes, you are having the electric potential. The same way you are having here magnetic potential also, isn't it? Now, to understand, isn't it, this magnetic potential, isn't it, what it is, etc. Now, let us take what it is an example that, isn't it? This, isn't it, already you have studied in PUC level, I think what is the first year PUC. Every, what is a body, isn't it? Every body, isn't it, material body, it has the two types of energies, potential energy and kinetic energy. Then potential energy formula is what? Isn't it? Potential energy EP, it is equal to mgh, isn't it? Now that is, suppose this is the surface of the earth and this is the body of mass m, which is at a height of h from the surface of the earth. Then potential energy here EP is equal to mgh, mass of the body, height of the body from the surface of the earth, and g is the what is the acceleration due to gravity, we say. But here you know that the earth has the gravitational field, earth's gravitational field, isn't it? And this what g, it is also be known as what it is the earth's gravitational field also. Then here, yes, a body, material body is having, isn't it, the gravitational potential energy or gravitational potential, isn't it? Now, for example, in this case, we see that if g is equal to 0, isn't it? If g is equal to 0, then what is the potential energy? This is equal to 0, isn't it? This is the potential energy, or we call it as the gravitational potential energy also. That means the body has got gravitational potential energy because of the gravitational field only, isn't it? If there is no gravitational field, then there is no gravitational potential energy. Now, for the simplicity, instead of saying gravitational potential energy, simply we pronounce as potential energy, isn't it? But its exact meaning is that every body has gravitational potential energy in the gravitational field, isn't it? Similarly, isn't it, in the electricity, every electric charge has electric potential in the electric field, isn't it? Every electric charge has electric potential in the electric field. In the same manner, isn't it? Every magnetic pole has magnetic potential in the magnetic field, isn't it? Now, I think if I write here, then you can understand very easily, isn't it? Every body has gravitational potential energy in gravitational field, isn't it? This gravitational potential energy in the gravitational field. Similarly, what is the every electric charge? Electric charge has electric potential, electric potential in electric field. In the electric field. Similarly, isn't it? Every magnetic pole has magnetic potential in magnetic field. This is the thing. We can what is the understanding? Isn't it? Now, in every magnetic field, a magnetic pole has the magnetic potential. Isn't it? Then let us think once again. This is a magnet, and if this is the magnet field, it produces the magnetic field. At any point in the magnetic field, when you put a magnetic pole here, it has magnetic potential. That is what we say. Every magnetic pole has magnetic potential, isn't it, in the magnetic field, isn't it? Now, when you place a magnetic pole in the magnetic, what it is the field, it has the magnetic potential means how much magnetic potential is there, isn't it? Now, to define it, that has been defined as listen here. Now, suppose if you consider this is the point of infinity, isn't it? One by one, listen here. Magnetic potential at any point in the magnetic field. Magnetic potential at any point in the magnetic field, it is equal to the work done, isn't it? Work done in bringing a unit north pole from infinity to the point against the field. Once again, I repeat, magnetic potential at any point in the magnetic field, it is equal to the amount of work done in bringing a unit north pole from infinity to the point against the field, isn't it? Then here, which will be taken as the point of infinity? I think I had made it clear that the point where the magnetic field is zero, the point where the magnetic field is zero, that point is taken as the what is the point of infinity. Now, if you are having the magnet here, this magnet produces the magnetic field only up to a certain extent. Beyond that, you never find the magnetic field. If there is no magnetic field, means that point where the magnetic field is zero, then that point is taken as the point of infinity. Then, in order to bring a unit north pole from here to here, whatever the amount of work has to be done, then that much amount of work is known as the magnetic potential. Then against the field means if the magnetic direction of the magnetic field is in this direction, you are bringing opposite to that. That is nothing but it is a against. Yes, this is the definition of the magnetic potential. Once again, I repeat here, is it magnetic potential at any point in the magnetic field, it is equal to the amount of work done in bringing a unit north pole from infinity to the point against the field. Then this is the definition of the magnetic potential. Now see, these are the four important properties of a magnetic dipole. Then first we have discussed what is the dipole means what. Next is magnetic field, magnetic intensity and magnetic potential. Now after understanding all these important properties, in the next class we are going to derive the formula of what is the magnetic intensity at any point on the axial line of a dipole, next on the equatorial line of a dipole, next the formula of the magnetic potential at any point due to a magnetic dipole. All those formulas we will derive and discuss in the last class. Thank you. I will stop here.